Hello, I'm Minjung Lee, the second semester of the master's course in Artificial Intelligence at Korea University. I'm gonna start my research presentation. The project title is Prompt-Driven Pruning of the Text-to-Image Diffusion Models for Improving Efficiency. This slide about research introduction. I'm studying to improve the efficiency of the model by reducing the number of parameters and the amount of computation by pruning the diffusion model based on the text prompt in the text-to-image task. The research goal is to propose a novel framework that uses prompt-based pruning techniques to increase the efficiency of diffusion models in text-to-image generation tasks. So I aim to improve the computational efficiency of the model by allowing the pruning process to be applied fluidly according to the prompt. The motivations behind my research stem from two main challenges in diffusion-based text-to-image generation models. First, these models are known for requiring high computational cost and substantial GPU resources, especially when they are used at the large scale. This is primarily because diffusion-based models rely on iterative calculations across multi-steps to generate images. Each iteration adds up, resulting in a significant increase in computational requirements. Due to this repeated nature of computations, these models demand more robust and powerful equipment to meet latency requirements and ensure the models work efficiently. Reducing the latency while managing such high computational loads can be extremely costly and resource-intensive, making it a critical area for optimization. The second motivation comes from the limitations of existing pruning strategies when applied to diffusion processes. In typical deep learning models, pruning is a common strategy to reduce model complexity by removing less important neurons or weights. However, in diffusion models, the process is more intricate. Diffusion-based image generations involves complex interactions between different components in each step of the diffusion process, meaning that simply applying conventional pruning techniques doesn't yield significant gains in efficiency. These interactions make it difficult to reduce computational loads effectively without compromising the model's performance and accuracy. Therefore, traditional pruning approaches fall short in this context, underscoring the need for a more tailored approach to pruning in diffusion-based models. Motivated by these two challenges, the high computational cost and the limitations of conventional pruning methods embarked on my research. So my goal has been to find ways to make diffusion models more efficient without sacrificing quality. Now I'd like to give a brief overview of the progress I've made so far in my research. Before diving into my specific approach, I will begin by presenting two papers that have been particularly valuable to my studies. These two papers provided foundational insights and helped shape the direction of my research. Once I have reviewed these papers, I will share the progress I've been exploring to address the challenges of improving the efficiency of diffusion-based text-to-image models. The first paper to be presented is Structure Pruning for Diffusion Models. This paper is published in 2023, which proposes a new pruning criterion to evaluate the importance of weights at each time step to apply structure pruning to diffusion models that can effectively reduce the model size by removing unnecessary parameters and substructures from the network. Let me explain the method for this. To evaluate the parameter importance in the model, the proposed method aggregates the effect of setting the value of each individual weight to 0 in the expression utilizing Taylor expansion and uses it as the final importance. And based on the obtained importance value, they address the pruning problem, for which they use a simplified pruning method by introducing a weighting variable, alpha t, which takes only one value between 0 and 1. To avoid pruning the time step t that generates the critical contents, they introduce a threshold large T based on the relative loss of LT over Lmax, so that the time steps below this threshold are considered uninformed, setting the alpha to 0 and pruning in the model. I'll explain the result. As shown in the two tables at the bottom, the scratch learning to train the weights of the model from scratch requires more steps to convert, and the pruned model achieves a relatively better FID score. So it indicates that the pre-trained diffusion model is more efficient. In addition, the experiments with the LSU and Church dataset show that the proposed method can converge and produce consistent results with only 10% of the pre-trained model, which requires a lot of time and resources through approximately 4.4 million training steps and lightweight parameters alone. This paper proposes a new pruning method to solve the problems of existing pruning methods caused by complex interactions in the diffusion model, and I think it is a good paper to study about my research topic in that it improved efficiency while maintaining and improving the production quality of the model. The following papers are published in 2023 CVPR. When applying structure prune, use dependency graphs to analyze the dependence of parameters on different neural networks structures without being limited to specific neural network structure, and propose a general approach to perform efficient prune based on it. I studied because I thought I could apply a unit of pruning structure to the diffusion model in that they set it as a dependency graph and applied it to several networks. Next, I will explain how to do this. To model the dependency graph, they generate the dependency graph generated by the defined interlayer and intra-layer dependency and infer the overall dependency. So here, the interlayer dependency refers to the dependence between input and output in the connected layer, and intra-layer dependency is defined as the dependence that occurs when inputs and outputs share the same pruning method within the same layer. Based on this dependency, they grouped the associated layers into a group and prune this group as a unit. Here, rather than evaluating the importance of parameters within a group individual, they proceed through the sparse training method, which introduces a normalization term to calculate the importance score of the group as a whole. Subsequently, the relative importance score is used to identify and prune the parameters of low importance within the group. Let me explain the results. The proposed method is used in both the experimental dataset Cypher 10 and Cypher 100, compared to other optimization methods that increase speed at the risk of performance degradation. Both performance and speed have improved. In addition, the highest accuracy was achieved when sparse training was used using the group structure, so pruning was carried out in consideration of the dependence relationship between groups. So they show that proposed method can minimize performance loss and efficiently reduce the weight of the model. In diffusion models, rather than simply reducing the number of time steps, it's essential to consider structural pruning of the model's parameters. Let me explain why. Diffusion models gradually generate images over multiple time steps, while reducing the time steps can indeed lower the computational load. It can also make the image generation process less refined, which may lead to a drop in image quality. In other words, while reducing time steps might improve efficiency, it's likely to impact the model's performance directly. Because of this limitation, I need an alternative approach to achieve efficiency without sacrificing quality. This is where parameter reduction through structure pruning becomes crucial. Structure pruning focuses on removing specific structure units within the model, such as filters, channels, or blocks, rather than individual parameters. This approach helps reduce computational complexity while maintaining the overall structural consistency of the model. Moreover, structure pruning allows us to streamline the model while preserving its original structure, minimizing potential performance losses. Now let's explain the advantage of using dependency graphs to define parameter groups and pruning on a group basis. First is preserving model consistency. A dependency graph visualizes how different parameters are interconnected and how they collectively contribute to specific operations. By pruning based on this graph, it can retain the primary computational paths within the model while removing less critical ones. This helps reduce unnecessary computational while preserving the functional consistency of the model. The next is minimizing performance degradation. When it prunes parameters in groups based on the dependency relationship, it can reduce unnecessary computational with minimal performance degradation. Unlike random removal of individual parameters, group-based pruning helps retain the core functionality of the model, making it linear without significant losses in accuracy. The last is enhanced parallelization and memory efficiency. Structure pruning based on groups simplifies the data flow within the model, making it more suitable for parallel processing. This optimization is especially beneficial on high-performance hardware like GPU or TPUs, where it can reduce resource consumption and increase processing speed. For the progress of my research, I'm using Stable Diffusion as the base model. The pruning structure I'm implementing is based on group units defined by a dependency graph. Through this approach, I can identify and remove parameter groups with lower dependencies, simplifying the model's architecture while preserving its essential functions. To achieve the sparsity ratio seen in previous papers, I am conducting experiments using the Cipher-10 and Cipher-100 dataset. Additionally, I'm implementing an importance score function to calculate the importance score, which will serve as the basis for pruning at the group level. This is it for the presentation of my research I prepared. So if you have any questions, please contact me by email at the bottom. Thank you.